that in here and it should be good. Alright, here we go. Seems a little bit tough. We'll be fine. Just a little extra speed. There we go. Alright. How does this now look? Oh no! Oh, what have I done? I've forgotten to put the butter. Oh, even if I put it in now, I've ruined the creaming process. Or have I? Well, let's try this. So, I was baking some Snickerdoodles the other day, and I made a bit of an oopsie. When I was creaming the wet ingredients together with a hand mixer, I forgot to add the butter. I was able to add it after I had already added all the dry ingredients into the mixed wet ingredients, but I was worried it would negatively affect the texture, since the creaming process helps separate the sugar crystals and incorporates air into the mixture. Maybe doing that with the eggs initially was enough? But, I thought to myself, why not make another batch correctly and have some others test them out? On the other hand, though, I wasn't too worried about incorporating the butter later, since the eggs already did a bit of the work, and butter can be incorporated into other doughs like brioche, where you slowly add a lot of butter to an already egg-rich dough. I was making some other baked goods for gathering later that night, so I had some other cards ready for some friends to give their feedback on, which I'm doing as part of a series of ongoing projects. The feedback cards consisted of a 5-star rating system for each recipe, as well as an optional nickname people could put down for matching with future experiments. Nothing too complicated or unfamiliar, since that would hurt an already limited sample size and possibly impact data quality. To make sure that the correctly creamed Snickerdoodles were easily identifiable, I added some purple and black food coloring so that they would still look reasonably appetizing in the normal to dim lighting of where they were to be served. I wanted it to be easy for people to know which cookie to mark on their sheet, as well as enticing them to eat both out of curiosity. I put out the baked goods at the gathering, where some others coincidentally brought food as well, though my food was the only one with the ratings cards that I put around the table, with recipe information and questionably visible signage on where to put the responses. After returning home, I entered the responses into a spreadsheet. Looking at the data, I had 6 pairs of responses that tried both cookies. Not a lot of data to work with, but I figured I could see if there was a statistically significant difference between the 2 cookies with the paired t-test. Alright, statistics time. When you want to know if the average of a group of numbers is different than another number, you can use what's called a t-test. It was originally created to make beer taste better, but you might use it, for example, to test if the average length of a subway footlong is at least 11.5 inches, which is my definition of being close enough to a foot. Or you could try to see if one Chipotle location has a larger average portion size for their steak when making burritos than another one, or if they're giving you at least the 4 ounces they advertise. My inflation-fueled fast food grievances aside, in my case, I want to see if the difference in ratings between the 2 types of Snickerdoodle cookies is significantly different. For this, I can take the differences of the scores for each person and run a t-test on them. Taking the difference turns 2 variables into 1 variable, and we can do this since the ratings are associated with the same people. This is called a paired t-test, and there are a few steps involved. Step 1. Define what you are trying to test. In my case, I am mostly concerned if my mistake results in a lower average rating. Formally, this means our null hypothesis is that the mistake either does nothing or improves the average score. The null hypothesis is just the default assumption which, if you can't reject, you go, yeah, this data doesn't really prove anything. Step 2. Calculate the mean of the data. This is the average of the sample, so we just add everything up and divide by the sample size. In our case, the sum of the differences on the cards is 2, and with 6 data points, that means that the average rating is 1/3 of a star higher for the incorrectly creamed Snickerdoodles. Step 3. Calculate the sample standard deviation. The standard deviation is a measure of how wide a probability distribution is, or how spread apart data are from each other. For example, the bars on these blue and red bell curves span one standard deviation on each side of their centers, which covers 68% of the area or 68% of the probability of their distributions. The 68% number is more or less unique to this specific shape, but in general, a good chunk of data is found within one standard deviation of the center. To calculate it, for each number in the dataset, you subtract the mean from it, and then square that difference. You add all of those squares together, and then divide by one less than the sample size. This number is called the sample variance. Then you take the square root, and it becomes the sample standard deviation. The reason for dividing by one less than the sample size instead of the sample size is that something funny happens when you estimate both the variance and the mean, and dividing by the sample size minus 1 instead of the sample size removes bias from the estimate. Normally it's represented by the lowercase Greek letter sigma, but when we make a sample estimate with dividing by n minus 1, we just use the letter s. Step 4. Divide the sample standard deviation by the square root of the sample size. This is the estimated standard deviation of the average of our sample. That is, if we kept on getting sets of 6 responses from people rating the cookies, we'd expect this standard deviation to describe how wide the averages of those responses are. Note that this animated visualization of those 6 red dots being average is a bit of a generalization, since we can only have integer ratings and differences, while the dots can be fractions, but it highlights how the sample average is roughly shaped like a bell curve, and about 68% of the data is within that pink horizontal bar. Step 5. Subtract the null hypothesis value, in this case 0, meaning 0 stars of difference between either cookie, from the average of the sample, and divide that value by the standard deviation of the average. This is the t-statistic that a computer will calculate the p-value for. The reason it's called the t-statistic is that it's distributed according to the t-distribution. It looks kind of like a bell curve, and actually approaches one when you have a large sample size, with its parameter Greek letter nu, the number of degrees of freedom, being equal to 1 less than the sample size you have, which is the same number you divided the sum of squares by to calculate the sample standard deviation. Technically, you should have normally distributed data when running the test. It's a specific shape of a bell curve, but generally, according to the central limit theorem, if you have enough data, it doesn't matter, since the average does approach a bell curve in that case. And if your data looks remotely bell-like, you'll probably be fine even for smaller sample sizes. Our scale theoretically spans up to 9 different values, -4 to +4 in terms of differences of star ratings, though we only see values from -2 to +2. This does fudge our numbers a little bit, but we'll pretend that it doesn't. Plugging the numbers in, we get a t-statistic of 0.5971 with 5 degrees of freedom, since we have 6 paired samples. Step 6. Because I'm only interested here in the mistake worsening the result, I am performing what's called a one-sided test. The left plot shows the t-distribution probability density function, or PDF, and the right plot shows the cumulative distribution function, or CDF, which is equal to the red area under the PDF. This is the probability that the t-statistic, represented by the red dot, is less than or equal to that value. Here we get 0.71, or 71%, meaning that there's a 71% probability that we get a result at least that low if the 2 cookies had the same mean, which is the baseline for the comparison, and an even greater probability if the faulty ones were better, though we just kind of ignore that. This 71% is what's called a p-value, and its definition is basically what I just described. It's the probability that we'd observe a result at least as extreme as the one we observed if the null hypothesis is true. In this case, the extremeness is measured from the far left of the t-distribution, so the lower the t-value, the lower the p-value. And the higher the t-value, the higher the p-value. Normally, we'd look at a cutoff of 5% for declaring a test significant, meaning that if there were no difference, only 5% of the time we'd observe a result at least that extreme. Now, since the average difference was higher than 0, we'd already be able to say that the test failed to reject the null hypothesis without plugging anything into a computer, since the p-value would be over 50%. But let's say when we originally wanted to construct the test, we wanted to see if there was any difference, positive or negative, in the mistake I made. Then we'd use what's called a two-sided test, where we consider the extremeness how far away from 0 the average is, which is the same, probabilistically speaking, as how far away the t-statistic is from 0. For our data, anything that is at least as extreme is represented by the area to the right of our statistic, which is marked by a red dot, as well as the area to the left of our flipped statistic, marked by the blue dot, since it being negative is just as interesting or extreme as it being positive for any given magnitude. The two-sided statistic can be calculated as 1 minus 2 times the CDF minus 0.5, where the CDF is just the cumulative probability measured from the left side. If the statistic were 0, we'd have a p-value of 100%, meaning that it can't get any less extreme. Even in this case, our p-value is 0.58, or 58%, meaning we can't discern a statistical difference between the two scores. This test can easily be done in any modern data analysis software. In R, it's literally just a function called t-test. In Excel, you can use these formulas to calculate one- and two-sided statistics. Pause here if you want to take a closer look. Note that I don't use Excel's built-in t-test function for the one-sided statistic, since it doesn't let you choose whether you're testing if your statistic is less than or greater than the target value. It just assumes no one would bother running a test when your average has the wrong sign and your p-value is obviously over 50%. As a quick summary, here are the steps in a more formal math notation, which are calculating the mean, the sample variance, the sample standard deviation, and the t-statistic. You can pause here if you want, but I'm yielding the extra 50 seconds the rest of this section would have taken back to the remainder of this video. Do note that you should not run multiple tests unless you plan for it in advance, and make appropriate adjustments in your p-value cutoffs to account for the fact that as you run more tests, some of them will pass by random chance. The simplest correction to do is to divide your target p-value by the number of tests you are running, which is known as the Bonferroni correction. There are other ways of approaching this, but they are usually more complicated. Now, you might be thinking, I guess this proves that it doesn't matter how you mix butter into Snickerdoodles, which is not the correct interpretation. From a statistical point of view, I failed to reject the null hypothesis that it made a difference. This is kind of a boring result, but it just means that you don't have enough data to detect differences, or that the effect you hypothesized just doesn't exist. Now, you might be wondering, how many cookies would I need to bake to get better results? A low sample size is a possible culprit here behind the high p-value, and these results really don't say that much. There is a concept called statistical power, which in our case is the probability that your test rejects a null hypothesis under a specific set of conditions. For example, if I thought the cookies I messed up would have an average rating of 3, the good cookies an average rating of 4, and a standard deviation of 1 for their differences, then I'd only have a 35% chance of correctly rejecting the null hypothesis. I will discuss in my next video how many cookies I need to make and have rated to do this in a more detailed discussion about statistical power, but I can say that it is quite a lot. There's also the fact that there are a lot of other factors that go into making the cookies, like how much they were mixed, the amount of time in the oven, and how much love you put into them. And the fact that I dyed one of them may have affected perception to some degree, or the order of consumption may have affected their perception. Or maybe the way people differentiate with star ratings isn't 100% consistent across people. Generally, a larger sample size can allay some fears, especially when the raw effect is larger, but inherent bias in the experiment can sometimes obfuscate the truth. Anyway, my sample size was small, but at least my fears of not creaming the butter correctly were put to rest with the actual data I had, since the actual people that ate them enjoyed them. And I tasted the cookies myself, and they were, well, alright. Which arguably is the only test you really need, the taste test. Thanks for watching. Don't forget to like and subscribe if you want to learn more about statistics and data science through whatever I decide to make more difficult and fun than it needed to be. Cheers!